If you've ever heard programmers talk about NP-complete problems, it probably sounded mysterious, intimidating, or overly mathematical. The term gets thrown around in interviews, research papers, and computer science discussions as if it represents a kind of mythical dragon. But underneath the jargon, the idea of NP-completeness is surprisingly intuitive. It's about problems that are easy to check but incredibly hard to solve. When computer scientists talk about the difficulty of a problem, they mean, how long will it take a computer to find the answer as the input grows? Some problems stay easy no matter how large the inputs are. Sorting a list or finding the biggest value in a list all scale nicely. But then there are problems that begin simple but quickly blow up in complexity. Double the input size, and the time required may explode exponentially. This gap between easy to verify and hard to compute is the heart of NP-completeness. To understand NP-complete problems, we need to understand two groups P, problems we can solve quickly. These are tasks where computers can find an answer efficiently, like finding the shortest route between two connected cities or searching for an item in a sorted list. 2. NP, problems we can check quickly. These problems may be extremely hard to solve, but once you're given a solution, you can verify it instantly. For example, imagine a giant Sudoku puzzle. Solving it might take you hours, but once someone shows you a completed grid, you can check whether it's correct in seconds. The checking is easy category is NP.
Inside NP, there is a special set of problems known as NP-complete. These are the boss-level problems, the hardest of the hard within NP.
They're incredibly hard to solve, and no one has ever found an efficient method that works for all possible inputs. If we ever solve one of them efficiently, we could solve every single NP problem efficiently. This is what makes them legendary. Think of NP-complete problems like trying to find the right key for a massive, messy ring containing billions of keys. Finding the correct key means you may need to try thousands, millions, or billions of keys. There's no obvious shortcut. Checking that a key works is instant. Stick the key in the lock. If it turns, you're done. Famous examples of NP-complete problems include the traveling salesman problem and the knapsack problem. The traveling salesman problem asks to find the shortest tour through many cities. The knapsack problem involves picking the most valuable items without exceeding a weight limit. Why NP-complete problems matter in real life? They aren't just theoretical curiosities. They control the shape of industries. From logistics and delivery, finding optimal shipping routes, to cybersecurity, where many cryptographic systems depend on these problems. Scheduling, search engines, and even drug discovery and biology all encounter NP-complete challenges. The central question is solving problems fundamentally harder than checking them? This is the famous P versus NP problem.
If we ever discovered a fast algorithm for any NP-complete problem, it would mean every NP problem becomes easy, encryption collapses, and massive scientific breakthroughs arrive overnight.
Despite decades of research, nobody has proved whether such shortcuts exist. How we cope with NP-complete problems today. Engineers rely on heuristics, approximation, randomization, and special cases. We can often find excellent solutions in practice, just not guaranteed optimal ones. NP-complete problems represent the boundary line between what seems possible and what might forever remain beyond reach. They are the puzzles for which the answer is easy to recognize, but the path to the answer is a labyrinth. Understanding NP-completeness means understanding the limits of computation itself.